Ever wondered how your phone case, bottle cap, a chair, or even tiny precision parts inside machines are made? Spoiler, they all start as little plastic pellets. Welcome to injection molding, the fast, fiery, and fascinating process that makes billions of products every year. Back in the 1800s, billiard balls were carved from ivory, from elephant tusks. That was destroying elephant populations. A maker offered a $10,000 prize for a substitute. John Wesley Hyatt developed celluloid, one of the first plastics, and built an early molding apparatus to shape it. He didn't win the prize, but he set the stage for injection molding. Today, that idea has become one of the most important manufacturing processes on the planet. Think of it like making chocolate in molds. Melt it, pour it, let it cool. Except instead of chocolate, it's molten plastic under huge pressure. If it's plastic and has a shape, chances are injection molding made it. Now let's walk through the 5-step process. Step 1. Feeding. Snack time. The process starts with tiny plastic pellets. Think of them as cereal for the machine. Pellets may be mixed with colorant, or up to 15% recycled material. Step 2. Melting and mixing. The heat is on. Pellets travel into a heated barrel, where a rotating screw churns them like a blender. The screw both mixes and helps melt the plastic into a thick, uniform molten mass. Step 3. Injection. Under pressure. When enough molten plastic collects, the screw shoots forward like a plunger, blasting the material into the mold in seconds. Step 4. Cooling. Time to chill. Water channels in the mold quickly remove heat so the plastic solidifies into shape. Cooling time is a major cycle constraint. Step 5. Ejection. The big reveal. Ejector pins push the finished part out with a satisfying pop. Early machines used plungers and suffered from uneven heating. The center too cool, the outside scorched. The solution was the reciprocating screw. The screw does 3 game-changing things. It thins the plastic layer for more even heating. Its flights transport and mix the pellets. And the shear from the screw produces most of the melting heat, often 60 to 90% of it. That invention revolutionized plastics manufacturing in the 20th century. The mold itself is a precision tool, steel, machined to microscopic tolerances, and often costing tens or even hundreds of thousands of dollars. When molten plastic fills the cavity, trapped air must escape through tiny vents. Channels only a few microns deep. The plastic's viscosity keeps it from flowing through those vents, but air gets out. When the mold opens, suction initially holds the halves together. That's why molds open slowly a few millimeters to let air in, then open fully so the part can be removed safely. Once cooled, plastic shrinks and grips the core. Ejector pins push the part away and often leave small circular witness marks you can spot on many items. For larger single parts, a sprue connects the injection unit to the mold. For multi-cavity molds, a sprue feeds runners, a network of channels that deliver molten plastic to each cavity through small gates. That's why model kits often arrive still attached to runners. Where 2 mold halves meet is the parting line. You'll often see it as a faint seam. Designers add tiny draft angles, sometimes as little as 1 degree, so the part can release without scraping the mold walls. Instead of a toy example, let's look at a real technical part. An electrical connector housing. The tiny, precise plastic shell that holds metal contacts in plugs, sensors, and control modules. These parts require tight tolerances, clean surfaces, and no extra plastic to chop off. Manufacturers often use hot runner systems for this. A heated distribution network that keeps the plastic molten until it reaches each cavity. Hot runners reduce waste since there are no sprues to trim, and they provide consistent filling for many cavities. That consistency is critical for electrical parts that must fit metal contacts precisely. Designers hide draft in internal ribs and geometry, so outer mating surfaces stay square and accurate while still allowing clean ejection. Sometimes molds include removable inserts, like date wheels or part-specific inserts, so production runs can be tracked, or small internal features swapped without remaking the whole mold. This process produces everything from toys to critical technical components used in electronics, medical devices, and automotive systems. Injection molding is how we get mass precision at low cost. And with the right mold and machine, a finished part can be produced in under 10 seconds. That's the difference between artisanal and industrial-scale manufacturing. John Wesley Hyatt's celluloid ball may not have won the contest, but it launched a revolution in how we make things. Tiny pellets, precise molds, and machines that do the heavy lifting. So next time you look at your devices, or the tiny components inside them, remember, injection molding turned raw pellets into the precise plastic parts that make modern tech possible. If you enjoyed this behind-the-scenes look, hit subscribe and join us for more stories about the stuff our world is built from.